Quiero pasarle.
Nada más.
Ok.
Puedes tomarlo, puedes pararte,
Puedo hacer eso.
lo que quieras.
Muchas gracias.
Solo que tendrías que...
Sí, mira, no,
Ajá.
sí,
Exacto.
take time. Okay, very clean.
The afternoon session now. With two presentations. The first one by Max Fernandez de Castro from the Universidad Metropolitana. Thank you.
Well, thank you very much to the organizer for the invitation, myself included. And I'm going to talk about the short disease and what it is, and why I hope to make clear why it's important as a subject. First of all, what is short disease? Short disease is a number theoretic function from natural numbers. It's effectively confirmed if an argument is recursive or a prime variable or calculated by a two machine or lambda the value. And in the last times, some years ago, has been discussed very profoundly information what the thesis says when it is true or false, or in many cases where the evidence or at least stability beyond sometimes it's it's true, but it cannot be because mathematical from a mathematical point of view. And to begin, I'm going to say what exactly I am going to talk about. I am going to talk about the short thesis as an explication. The explication is a kind of Carnavian sense. The term is a very original or single definition, and you say there's meaning that it's still the constellation of a single but it's a means that the situation that corresponds for this of the organisms and rigid notion technically. This is very common in science. We talk the limitations in natural language, both the scientific study will not be a precise definition that can be used in scientific theory. Okay, then if it is an definition, I will say that it's true or adequate to the extent that it's explicable. That's a concept, scientific concept, is scientifically useful and corresponds with Okay. To be clear what I'm going to talk about, simply explicando el software, because there are people who has said, who have said that it is true, or that it is false, etc. And this is because there are some ambiguity in the use of terms. What is exactly the explicando? What the explicando? What is the implicit notion that we are going to try to define in mathematical terms? And sometimes it's thought as something that has to do with the capacity of machines, the physical machines. Sometimes with the capacity of the human. There are some discussions in of time, in philosophy of mind about this. But for me, the most important is the capacity of a human calculation. Hobbes has found that neither Charles nor Turing originally in 1936, and they formulated the text in this process, were working or thinking about physical or abstract machines. And it's very clear in George's first paragraph, in French article. He says, the purpose of the present paper is to propose a definition of effective calculability, which is sought to correspond satisfactorily to the somewhat vague implicit notion in terms of which problems of this class are often stated, and show by means of an example that not every problem of this class is solved. Okay. To understand that, I should mention what are these problems that he had mentioned before, and I give two examples. Okay, in mathematics, it's very often that some problems are posed in terms of finding an algorithm or a decisive method or calculable or a calculation and algorithms of many calculations in all this history of mathematics. And some of these problems were precisely formulated only in 1930s, when the definition of algorithm was written. Okay, for instance, two of these problems are given a Diophantine equation with any number of unknown quantities and with rational integral numbers to devise a process according to which it can be determined by the finite number of operations where the equation is solvable in integers. And it was one of the famous Hilbert problems in the beginning of physics. And other one also formulated by Peter in 1928 is there a mechanical procedure that we can determine in a finite number of steps whether any given logical formula is universally valid. And this is also a very famous known as the Chinese problem. And Klein and George and Turing were dealing exactly with this problem. Then we are dealing with something that is mathematical and has to do with the mathematical facts. What is an algorithm for a mathematician? And this is important. For instance, I took this example. The teacher says to the children, please add the numbers from 1 to 100. And they began to do the algorithm, the addition. For cars, the physical results finds a way quickly give the answer. And what is that? That's an algorithm. He is doing the next, the other children are not doing it. Then, to know what is an algorithm is an important point for the students, from the point of view of mathematical facts. Okay, there are two easy arguments. What has been called the confluence of ideas. This is Gandhi, that has studied very well this the history of this point of this subject. There are several important logicians, mathematicians that have given a formulation of what is an algorithm. They gave this characterization almost at the same time. They arrived at different concepts, but these concepts are equivalent from the statistical point of view. They gave place exactly at the same set of functions. For instance, the triangulated, lambda calculus, the torch, the Turing machine, post, and all are at the same thing, 1970s. Then we can think that is a proof that they are capturing some fixed logic. Okay. Second, more counter example is enough. For instance, in 1928, the idea was that the notion of computable was captured by what is called now recursive primitive functions, but Ackermann has found a context. But they have new condition to avoid this context. And only there are two important arguments. And these arguments were given in the original arguments in which these divisions were posed. First argument that links arithmetical calculation with logical calculation, and Turing analysis of what it means to calculate, along with what was called later the squeezing arguments. The first George Gibbs gave two arguments. The first one is, they are very similar. The first one is, we suppose that we have the repeating notion of an algorithm. What does it mean to calculate? Or an addition? To put numbers, to pass one step to the other, only to resolve is obtained. And he supposes that these steps were so little, so easy, that can be captured by a recursive function. And the combination of these recursive functions gives us the recursive function that corresponds to this operation. It's a little bit circular, just a little bit, not quite. The second is links what is a calculation, numerical calculation with logic. And we can suppose that when we are following an operation, we are following rules of inference. We are inferring. And he thinks that he takes this definition. If I have an equation that gives me the value of a function for a certain argument, I will say that it's effective calculable if I can prove that in a system that has no idea. they know the symbols who makes a language that can allow us to express arithmetical functions. Then he says, if L, the logic we are using, satisfies conditions any system of logic must satisfy, established by Gary Princeton lectures 1934, then its rule of inference must be an effective calculable operation. The set of functions must be effectively enumerable. And the relation between a natural number and its corresponding formal expression must be effectively calculable. Then, suppose that each time we use effective calculable, he can say record. Again, there is a singularity. But if the system of logic has these characteristics, then the predicate theorem of L should be recursive and enumerable. That means the original function can be captured by a recursive function. What is interesting for me is that what happens if the logic has not these characteristics, one of these characteristics? It is this is the minimum that we need to ask for a logic to make arithmetic. And this was established by Gödel. But there are some presuppositions here in this argument. The first one is that logic must provide a calculus rationator. In this case, it should be possible to translate every valid mathematical argument into the logical language and prove that this formal argument is valid without any possible doubt. I am thinking in Leibniz, the idea of logic as something that must be algorithmic. Some authors have thought that logic originally, as it was formulated by Aristotle, does not need to be a canon. Then this is a supposition. And George said, if Principia Mathematica or others, for instance, Carmelo Frankenstein's system is omega consistent, I'm not going to explain what is that. And the numerical function is not general recursive, then whatever personal reversible choice is made of a formal definition of F within the system of Principia Mathematica. Therefore exists a positive integer A such that for no possible integer B is the proposition F R equal B, probably within the system of Principia. That is said in a letter written by George in 1967, in answer to a mathematician called SUHFECIM-UNAM, who tried to refute George's. And he asked this interesting paragraph. Therefore, to discover a formula which was effectively calculable, but not general recursive, that is to say, to refute short spaces, would imply the discovery of an utterly new principle of logic, not only never before formulated, but never before actually used in mathematical systems. Of course, to accept that, we should accept some presuppositions. One of them is this. But I quote this not only because it seems to be very interesting to link calculation with logic, but also to say that solstices captures something that belongs to mathematical types. Okay, the squeezing argument, this is very good argument. We take, this was given in 1968, I think, by Kreisler, and he tries to prove that, for instance, the notion, well, the concept, to be a theorem of nationalization of calculus, whatever there are many, and the notion to be valid in this sense. We have here also a concept beyond well defined, and here a notion. Then we take the concept arguments without arithmetic concept model. Only if we have an argument that has an arithmetic counter model, this cannot be valid. Or to say, in order to exact, this is the extension. So this is the concept and this is the extension. Extension of B is contained in B, extension of B is contained in A, then the PRS. Okay. Thank you very much. Okay, there is also a squeezing argument for shortening. This is a function that can be calculated by Turing machine. This is the intuitive notion to be an effectively calculable function. Only if we have an argument that is formally correct, is intuitive correct. And we need a concept such that every calculable function is included in this other concept. But we can prove that this concept and this concept have the same extension. The notion remains in the middle. This is why it's called the switching argument. Okay, and what is this concept? Well, it's called the Colmogorov of Ouspensky calculability, given at the end of 1969, something like that. And the idea is to give an algorithm relaxing some of the constraints of a Turing machine. For instance, in a Turing machine, there is only one dimension. We have to go the cells in line, and in each cell there is a letter, and we have to move and to change, delete, or write something. Seriously different because, for instance, the data states at every stage of the computation is a finite combination of cells, each with a symbol arranged in a network. And this network can be very structured in many ways. But all that is a relaxation of a machine. But even with this relaxation, we obtain exactly the same calculable functions. Then this is the squeezing machine that we know the remains Turing machine calculable and basically Colmogorov calculation. And as the extremes are the same extension, the intuitive notion falls. Okay, I'm going to finish. very quickly. Okay, what does it mean? That to defeat the argument, we should find an algorithm from an intuitive point of view that cannot be carried out by a cosmological space algorithm. I think that justice is true, but the truth allows us to explore the concept. For instance, Black and Clean have given some objections. For instance, they say, okay, but the calculator can make each state quickly with acceleration. Okay, that would be applicable to physical machines, but not a human machine. During analysis work and idealized human roles, when carrying out what we call a calculation. For me, it's important what we call, we are capturing something that is said from the image. Idealization means only that there is no boundary space for time. What are the basic constraints of an idealized human calculations that are included in the definition of a Turing machine? Bounded local inspection. Finally, many steps, the mind calculation. Discrete steps are absolutely determined by the symbol scan and the present state. A set of fixed rules given by a finite sheet or table. Okay, and what does it mean? An algorithm is always to give an instruction of something that can be communicated to a man who is inside the box. And that is very elementary in his mind. A little bit stupid maybe. What the man inside the box can do? Recognize symbols of a binary alphabet, move from a box to the next, and go from one state to another. I think this is what Hilbert called symbol intuition. This is the atomic, the simplest movements or operations that a human mind can do. Following an algorithm is not part of mathematics. That a mathematician reduces the complexity of algorithms, not always, sometimes, improving the existing ones. In that sense, short distance sheds light on a mathematical activity. Institutions. Short thesis refers to mathematical arguments of all kinds, not only concerned with a particular domain of mathematics. It accepts and implies that some important problems have been solved. For instance, if I don't accept short thesis, I can say that some of the problems I mentioned at the starting point are not solved, have not been solved. Second, two of the strongest arguments in its favor were advanced by Short and Turing in the seminal 1976 articles. The first narrowly related to technological requirements to provide a language where mathematical proofs can be translated and their validity verified by every human being. That doesn't mean that these arguments, the formal arguments, can be understood easily. We have too many trees, we don't see the forest. Both can be verified. The second argument is an analysis of an ideal human mind as it makes a calculation. In both sense, arguments for short thesis help us to elucidate some mathematical facts. Thank you.
Thank you very much. We have time maybe for one or two questions.
No, they are not.
Thanks, Max. I will pose this question, but maybe not for a short video. So when we talk about the stational comparison between two contact points in order to have different arguments for the new one, how do you define, how do you can say that two from opposite sides are extensional equivalent?
There is a demonstration in mathematical.
Mathematical reason.
You can verify that. I think the other squeezing argument is more interesting crisis argument. Both the idea is the same. And at the end, you can prove that these two extremes are extensionally equivalent. In the case of the first squeezing argument, it is the logarithm column. Very important result. Okay.
Well, thank you very much for the presentation.
No te vas a sacar ¿no?
Now listen to Eduardo Galderia de la UNAM. Thank you.
Thank you very much for all of you for attending this session. But special mention deserves the organizers for securing such a cool place for such an uncommon symposium. Now, the tone of the talk is divulgatory. Its aim is to give you a taste of what we talk about when we talk about the curricular correspondence, but its content belongs to the output produced at the lab of computational logic led by Dr. Pablo Miranda, and as well as Dr. Lourdes Gonzalez Weber. Now, for any practitioner of any scientific discipline, it's the hard task to give in a nutshell the scope and limits of his own discipline. But it is especially harder for the mathematician, as it is said that mathematics permeates all other sciences. Now, in a telegraphic and epistolary way, invariant has characterized mathematical endeavor as the interplay of three activities: defining, calculating, and proving. Now, for those who knows Grover's proof, this is certainly an echo of his intuitionistic philosophy, which, strictly speaking, he said, the construction of intuitive mathematics is an action, not a science. It becomes a science only when mathematical constructions themselves are treated as objects of a secondary meta-level investigation. Now, if we take together these two points of views, we see that we are moving the focus from mathematical truths, that is theorems, considered as finished results, to the constructive acts by which such results are obtained. And from this perspective, we can consider that proof is an act of providing evidence for a judgment. To prove A, which is a mathematical proposition, is to give a construction that warrants the judgments that A holds. The Kurikawa correspondence, in this sense, is making a precise structural relation between these three activities Barendek has mentioned, which are defining, computing, and proving, as we will see. Now, the previous point should be distinguished from the notion of valid consequence. Valid consequence, as we know, concerns the preservation of truth from premises to conclusion. In symbols, we have this set of premises from A to AN, and we say that this models the truth of B or entails B. Proof, by contrast, concerns the preservation of constructive evidence. From evidence for the premises, one obtains evidence for the conclusion. That is to say that if we have proofs of A to AN, then we can secure a proof of B.
Right.
The difference can be seen in a simple example. Now, on the left hand, we have what we can take as inference from a valid consequence perspective. From the right side, we have a proof, a proper proof. This is a complicated way using only minimal logic with falsehood to state that A and B entails A. Now, the distinction is subtle. Consequence concerns the preservation of truth between propositions, while inference concerns the passage from granted judgments to warranted conclusions. In Martin Law's terms, a valid inference preserves correct assertion or knowledge from premises to conclusion. The left hand side records only the consequence. Truth is preserved from premise to conclusion, but we don't know how the preservation takes place. As soon as Lorenz Fong has pointed out, this brings to the fore the phenomenon of blind influences, since the route by which evidence is transmitted is not displayed. From fact to consequence, for example, one needs to recur to additional machinery, such as converting the formula into a normal form, post-normal form. And this is just a section of the premise as we have seen. The right-hand side is free from this phenomenon of blindness, because what it uses is the premise according to its form. In this case, it is an implication. We can say in Gelson's terminology that the idea behind normal proofs is that proofs satisfy the formula property, which is in an informal way enunciated as this: no concepts enter into the proof other than those contained in its final result. Now, we can see from this perspective that proof is not merely a relation between propositions. Proof is primarily an act by which a judgment is made evident. By evident, I'm not talking about obviousness. Its function is to transmit constructive evidence from granted judgments to new judgments. In this sense, proof belongs to the activity of reasoning itself, as Haydn has put it. If mathematics consists of mental constructions, then every mathematical theorem is the expression of the result of a successful construction. The proof of the theorem consists in this construction itself, and the steps of the proof are the same as the steps of the mathematical construction. Haydn later clarifies the sense in which mathematical entities are created. We must be well aware, he said, that the verb to create has here another meaning than in creating a work of art. After being created, a painting exists in an external world, but this is not the case for the mentally created entity. Now, this has another side, which is the ontological side of proofs. A proof, we have seen, considered as an act, can leave a trace, either in our memory or in a communicable expression, such as a paper and pencil derivation, which records how the judgment was obtained. This is what Martin Locke calls the proof. The proof trace should not be confused with the proof object. The trace records how a judgment was obtained, whereas the proof object is the abstract entity generated and governed by rules. The issue, just to clarify, is not metaphysical, but foundational. Mathematical objects are not bare abstract stuff. In type theory, they are classified by types whose rule-governed behavior specifies how their objects are constructed, decomposed, or used. And this is a difference with respect with set theory. We can think of a type as a set, but unlike a set, types are only managed by their rules, by how we produce objects, how we manipulate them, how we use them. That is the extra stuff that adds the type theory perspective. This gives proof as the second aspect. It is not only an act of knowledge, but can also be studied as an object governed by rules of formation, derivation, and computation. The Curie-Howard correspondence makes these double aspects precise. Proposition corresponds to types, and proof objects to terms inhabiting those types. Now, the easy way to present the Curie-Howard correspondence is by giving the relation between two kinds of systems. One is natural deduction, which is a system for representing proof, and the lambda calculus, which is a system for the manipulation of and study the behavior of functions. So, as the title says, the happy marriage of natural deduction with the simply lambda calculus has three interpretations. The first one, which is a kind of slogan, is proposition as types. And this means that a proposition specifies the type of evidence required for its assertion. The second is that proofs as programs. A proof object of A is represented by a term inhabiting that type. In this case, we have an arbitrary R. The notation says that R belongs to A. It's an element. The third is proof simplification as program evaluation. Proof simplification and term for computation are the two sides of the same operation. Thus, the Curie-Howard correspondence as Wadler has size is not a Hartley rejection between systems, but it is a genuine isomorphism, and at least considering only the intuitionistic fragment that preserves the deeper structure of proofs and programs and simplification as evaluation. Now, this is to compare both. The first square is the Bacchus norm form for the rules of the lambda calculus. We have variables, we have lambda abstraction, and we have application. Below it, we have, this is the minimal propositional fragment of intuitionistic logic. Now, what we have, if we don't pay attention to the terms in red, we have the three rules of this system, which is on the top of it as the rule of assumption. Below them, at the left, we have the rule for introducing the implication. And for the logicians, the other one is the most known as modus ponens. Now let's give a review of these three rules. Now, assumptions are read as variables. That is the rule of assumption. And what we are saying here, or what it amounts to, is that an assumption is labeled or recorded as a variable. Now, the rule of invocation introduction corresponds to lambda abstraction. If there is a proof of B from the temporary assumption that there is a proof of A, then when we retract this dependency, we can generate a proof of A implies B. And the last one is the implication elimination rule, which corresponds to function application in the lambda calculus. If you have a proof of A implies B, then, and if we have a proof of the antecedent, we can obtain B, which is just the type, which has the function application type. Now, we can elaborate on this theorem. It is what Russell calls the principle of commutativity. If we have a proof of A implies B that implies C, then we can construct a proof that B implies A that implies C, which in this case is codified by these lambda terms. Now, in more graphic view, what we have is this kind of construction. As you can see, we have labeled all the premises from the, if we apply X, Y to X, we obtain this proof, subproof, which is labeled by XY. And if we have a proof of B, we have then a proof of, we can derive a proof of C. And if we discharge, this is the meaning of the brackets. We use them when we retract the assumption that we have a hypothetical proof. So discharging all the evidence, we arrive at the proof of the principle of commutativity, coded as a lambda term. Now, normalization in natural deduction consists in the simplification of proofs by removing their redundancies. A detour, that is the most basic kind of redundancy at this level, arises when an introduction rule is immediately followed by an elimination. And this is to construct the major premise of an elimination. From a computational perspective, what we have is that normalization is characterized by the vector rule. That is to say, when a function is applied by lambda abstractions, it is evaluated. It computes by substituting the argument for the bound variable. That is, we have a substitution of the assumption. We have a substitution of the assumption for the real proof of that was assumed as a hypothesis. And this is what the vector rule means. This is the point at which proof as fact, proof as object, and normalization as computation come together. We can look at this example. This is the canonical way to represent a detour. As I explained, we have, look at this proof. We have a proof of B. We start with a proof of B from the assumption of having proof of A. And look at the conclusion. We conclude B. So this complication is that assuming a proof of B from the assumption of having a proof of A and applying lambda abstraction or implication introduction, and assuming that we have a proof of A, not its assumption, we arrive at what we have started, the proof of B, in a more complicated sense. Now, when we apply the beta reduction rules, we can see what it was that we substitute the assumption of A by the proof of A. Now, schematically, the proof constructs this is an example of how we remove detours in this setting. This could be as complicated as we want. As you will see, this is a proof that only shows 3 detours, but look at the monster. Now, schematically, the proof constructs the identity function, which is if we have a proof of A, and discharging that assumption, we arrive at the identity. But immediately we are applying a proof of A. In this case, it is 3 times. So it's a little bit, the diagram is gigantic, so sorry about that. We have 3 detours. We have 1 here, we have another here, and when we resolve this, we are going to find out the other. So an application of the beta rule yields this. This is just to show where the beta rule was applied, which means that it was applied at the top leftmost. Then another application of the beta rule, we remove this pair of rules, and we arrive at this proof. And this is the other detour that I mentioned, that when we resolve this, it's going to appear this last one. We made another application of the beta rule, and we arrive, we could from the start, it was possible for us to conclude. This is just an illustration of the method. Now, for final thoughts, our journey from proof to computation is not just a technical curiosity. It shows that proofs have a dynamic. They are not inner certificates, but structured objects whose internal organization can be expected, transformed, and simplified. This brings us back to our starting point. Mathematics is a constructive activity. To prove is not merely to register something that is true, but to carry out a construction whose steps can themselves become objects of mathematical reflection. In this sense, mathematics understood demands more than a technical precision. It is thought itself, guided by an ever-present demand for conceptual clarity, a clarity that keeps our mathematical endeavor honest by making assumptions and inferential steps explicit. In the end, it is what Proverb says. It provides us with a precise inventory of the exactness in our thinking activity. Thank you very much.
Thank you very much. We have a few minutes for some questions for the participants.
Thank you very much. My question is it's a rather strange question, but still, it doesn't break what you said. Just, if I take any existence theorem in mathematics, for instance, there is only one complex binary that is a complex field. There's only one. And it's only where we may call it an action and a group. But where is the difference between calculating and proving?
Well,
you know the way it is again concept. You get one by option of the of 1942 and so on, which is extraordinary. It was considered as surprising and so on. We get to really other results. But here, what I mean is, it is something which is you cannot fully describe. It's very something. Once you accept a certain definition by my field, okay. But it exists. I mean, my proving is not calculating. It is the existence. Only that. Or, and this is another term, you cannot have, I mean, every complete, let's say, complete system field you can reduce to the real number system. Definition, okay, but, so proving is exact. There's no calculation, or which is a serious problem. Exactly what you said. If there is no calculation, your proof is an act, or your calculation is an act. But again, I try to understand. It's interesting, very interesting, but it's the way that we are. I mean, there are statements in mathematics which are ontological statements.
yeah.
Is it
If it is an ontological statement, then it is calculable. As I said, a calculation in the ontological part doesn't involve metaphysics or stuff like that. We are talking about how we manipulate objects according to rules. This is a procedural perspective on logic. The result of that activity is constitution. Proving, move on.
understand? I have difficulties in understanding that.
well, you should.
Yeah, okay, so,
You should see what the new investigation of Rabbit says around validity is hypothesized and yeah, and he's considering as a mathematical object, which is what people are ground. The ambiguity of proving as an act and proving as a process is everywhere in mathematics. However, this is just you want a tailored example because we are considering just minimal logic. But the Curry-Howard correspondence doesn't extend to any mathematical theory. It is useful and it is exactly what the computer scientist needs to create proof scripts and stuff like that.
Thank you. One last question. Thank you very much. Just a question about, when we were talking about simplifying, I think like, the proofs that we already have, but is there another research going on with finding proofs that are not prevalent in a systematic way to prove they have in calculus, calculus? Can it be done? Has it been done?
I think that would not be type theory, like in a broader sense. The only mathematical theory that incorporates explicitly with syntax the Curry-Howard correspondence is constructive type theory. Now, with constructive type theory, you can reconstruct, I don't know, all, but it is assumed that all of the existing mathematics. So these are processes, tools that we have it also in multi-type theory. It's just constructive type theory with a topological interpretation. And yet things get more complicated. The thing is that transpires here is that if we simplify proofs, the concept that we want to erect or make explicit is that of direct proof. Is like not using lemmas in a mathematical proof. It's like removing because you know how to, from the rules, you know how to arrive or at least imagine how to arrive to the intended result.
Thank you very much. Thank you very much, Robin, for the presentation. So we have now a 25-minute break, coffee break, 20 minutes, and we will resume for the last session of the day at 5:30.
So for the last session of this afternoon, we will hear Edgar de los Reyes from the UNAM.
Thank you very much. Buenas tardes a todos. Bonjour. Well, I want to start to say thank you for the opportunity to stay here. These events between Mexican and French are very great, and I am excited to share a bit of my work with you. Well, according to the topic of this seminar, I decided to talk about some examples of changing mathematical knowledge. I'm going to talk about 3 examples of problems or results in mathematics that mean change. Well, this is part of my work of PhD. The first example is about the scoring cycle. It's a problem from the 5th century BC. Construct a square equal to a given circle. Of course, there were many attempts of solution, but around this problem appeared the question: what means of solution are of not geometric? This is important because it constitutes the framework of the problem. In other words, the accepted tools and concepts for solving the problem. With this problem, the geometric framework was established in 1627 with Descartes' geometry. The idea behind this framework is exactness. That means a chord is geometric if there is an equation that expresses it. But this geometric framework is different from the first framework of the problem. We know this framework is Euclidean geometric. Finally, in the 19th century, the answer to the problem was given. A negative answer with the Lineman's work. It is impossible to construct a square equal to a given circle in a geometric framework. However, the answer and previous parts of solution are not in the geometric framework. Partial solution, for example, the Lambert's proof of irrationality of B. The second example is the Abel's impossibility theorem. The problem is find the general solution for the 5th-degree equation. This problem is very ancient, but in 1771, Lagrange, in his work Reflection to Resolution and Degree this equation, explored the methods now proved that and for solving an equation and develop a general method for solving them. Then, with this new method, he showed that it was not useful for solving 5th-degree equation. Thus, Lagrange established the framework for solving the problem of the 5th-degree equation. Since it would now be necessary to research the solution of the equation only through Lagrange method, and this is an algebraic framework. However, in 1824, Abel proved that it's impossible to find the general solution for the 5th-degree equation in this algebraic framework. Well, the third example is Gödel incompleteness theorem, the problem to prove the consistency of a formal system for arithmetic. Arithmetic, this means real numbers. In this case, the framework was established by Hilbert. Through several articles and lectures, over approximately 30 years. Part of this framework was axiomatic method in this arithmetic and metamathematics. This is the Hilbert program. But in 1921, Gödel proved that it is impossible for a system with specific features to prove its own consistency. Now, it's very important to note that Gödel's proof has all the characteristics established by Hilbert's program. Therefore, Gödel's proof is within the framework of the program. If we have three examples of problems with negative answer, but how does it mean changing mathematics? We will see this now. In the case of the squaring the cycle, in the search for a solution of this problem, it was necessary, in the process of the solution, it was necessary to approximating curve with a straight line. In other words, notion about the limit. Also, it was necessary in this problem, infinite arithmetic process. For example, continued fractions. Thus, this problem leads from geometry to new ideas that gave rise to calculus. In the second example, the Abel's impossibility theorem, in the process of the solution, it was necessary to understand the connection between algebraic operation and the solution of an equation. Thus, this problem leads from algebra to new ideas that give rise to model algebra. In the case of the example of Gödel's incompleteness theorem, in the process of solution, it was necessary to understanding the relationship between a theory, a formal system, or a theory and metamathematics. In this problem, Gödel made an interesting and creative method for relation three elements in a proof. Thus, the problem leads from logic to new ideas that give rise to proof theory. This is very important. Negative answers to these problems lead to a change of ideas about mathematical objects when a negative answer appears and coincides with to meet the thing in different ways about these problems, so the change arises. The negative answer to these problems lead to understanding important aspects of the related mathematical objects, which in turn led to the generation of new concepts and relations between them to new areas of mathematics. Therefore, I call these schemes of results cornerstones because they change the course of mathematical knowledge. The changing point by these impossibilities for solving problems is strong because it forces a change in the way of thinking about problems and related objects, thus obtaining a new perspective and a possible solution, presenting a range of a new implication, different from those that will be obtained in its original framework. From these new ideas, new areas of mathematics, and new approaches to solving these problems were derived for the series from the framework original. it's important, this example. It's true there are another kind of impossibilities. For example, the Euclid's proposition 1-7. If two straight lines construct from the ends of a straight line and meeting in a point, there cannot be constructed from the ends of the same straight line and on the same side of it to other straight line meeting in another point and equal to the former two respectively, namely each equal to that from the same end. The idea is short that there are in mathematics results with answer negative, but in these results there are an special particular kinds of theorems that need change in mathematics, like the three examples, previous examples. And of course, there are another ways to change in mathematics, but this is one and is very important, I think. And this. And thank you for your attention.
Thank you very much. We have any question if you have some.
Thank you. I am a little bit puzzled with what exactly do you mean when you mention the framework, which establish somehow the limits and possibilities. But let me start with the very last example you gave. Certainly, the proposition you showed says something negative. But I don't know if the problem behind is really the negative quotation. Oh, because it clearly said, not in the framework of the first book, but in the framework of the third book, that two theories interpret only in 2 points. That is speaking of fake, really. Now, why the you gives in book 1, the first book, this particular negative version? It has to do, I think, with the next theorem of this book. This book, theorem 8, which is the second theorem of converse theorem for triangles. So Euclid needs the negative version in order to propose his construction. Constructive proof means by superposition of the second converse theorem for triangles. Though I'm not sure to agree with you. Example of this proposition as a negative proposition. It takes this particular formulation, book 1, but I insist, it takes positive formulation in book 3. Okay, so that is. And another question related with this framework is that when you mentioned your first example, the property of the set, you mentioned at the very first moment you didn't know the framework. Somehow to say that there was no solution to this. I'm not very, it was not clear what you exactly mean by that. There is no Euclidean construction, the metric construction, based on the Euclidean postulates. That is true. But I think the very first one we used, I think, was not possible. a geometric construction, square equal to the city, that's 13%. Yeah, there's no doubt about it. No, never spoken to you, but I mentioned he was completely clear that his documents and the construction that are allowed to be made within this framework, this was not possible to construct the square equal to the zero. So I don't know if it is exactly what you mean, because if in the case the problem is somehow different to the other example you gave, example the solution of a political question. Because that which are what is exactly the framework for the solution of an algebraic equation at the end of the 18th century. That was somehow something that Lagrange tried to make it clear in the dimensions, but there was no doubt that this problem was clear exactly what was the framework for the solution of one the equations. In the case of the square of the circle, the framework was completely clear, very clear in axiomatic Euclidean axiomatics, and this is Euclid was a very good one for me. There was no possible to construct a square equal to a circle within this general framework. I don't know what you think about it.
Okay, thank you. First, this proposition, the 1.7, is an answer negative because in this form is right. It's true. Many results in mathematics, it's possible to write in negative form, but this example is good because the origin completed right in negative form. Maybe the other proposition we can write in negative form, but why he write in this form? That's not important in this moment. The important is so there are other kinds of theorem in negatives. And in this example, it's a negative one problem. But also the line of the concept of tools about this problem of the relation in this theorem, in this proposition, continuing after the proposition. It's different with the other examples. In the other examples, in one moment, it's necessary to change the concept, change the tools, and include new conception that in the origin it was considered. About the framework in the squaring the cycle, it's true in this problem it was very difficult to establish the framework. Indeed, until the 16th century, we have the framework, and in the first was very difficult, or the essential of the difficult is how do you answer if something is geometric or not? The answer is regards geometric. Yeah, this framework is very different on the other proposition, the other one, and the framework is in. But I think maybe this is in the beginning of course it was very difficult to show that something can do it. It was necessary many development for arrive the first attempt. The proof something can do it. The first proof, form of first proof can do it is the one that when he proved the can do it, the duplication of the cube. I don't know if I can answer.
Oh,
Thank you for your talk.
Yeah, thank you.
I agree with you about the creativeness of some moments in mathematics. The structure sometimes, the negativeness comes out something broken and something green. And in that sense, do you think that's something similar in mathematics and other sciences? No? Could be, we love to say that we are totally different, but in this part, I think it's really part of human creations. No? It forces you to think over the.
Yeah, thank you. I think, let me say in this word, the mathematician have an idea when he tried to do an journey. So in this case, the mathematics say, no, in this way, no, is the answer. If you want the answer to this problem, you change. I mean, look forward. Yes, it's like a mathematician speaking to the mathematics. Yes,
I have a semantic question. You see, you arrived by saying that there are a certain number of negative results in mathematics. Then if you look at square root of 2 is an irrational number. This is not a negative answer. This is to say that square root of 2 doesn't belong to the irrational number or belongs, that is happening to the complement of rational numbers among in Greek. Yes, it's alpha, almost. But in fact, when you think of it, you always have to think that there is some humor, some kind of joke in mathematics. Why do they call it almost? Because we work with something using logos. Claims that something is almost. That is something strong. Mathematicians are the ones to say we have possibilities, yes, but we can do something else. And this is quite positive. Just it seems to me that you have two ways of looking at things. But think of terms exactly one very negative or resulting way. Sometimes it's a positive. Descartes says that you have to think that if you have a polynomial with real conditions like that, there should be imaginary quantities. What are imaginary quantities? Now think of it. Is the problem was to reduce these imaginary quantities to complex numbers? Okay. There all most of the results about are in the negative way. Except there is a non-constructive which was given by Chrysler just before the Second World War, but in fact it was still among the 80s, saying that you can prove that a polynomial, given polynomial with real conditions, has complex root, which is enough to say that, which is a constructive root. That is, it says that when you have polynomial Pz of z, where Pz is not equal to 0, that is a root, then you can find close to z prime, so that P of z prime in actual value is strictly less than P of z. Strictly less is nothing else. You can prove there exists an alpha very close to one. So that in fact you can find PLC prime in models strictly less than alpha PLC. This gives you a construct a convergent result. It's no problem. So you can prove positively the existence of the root. In fact, the alpha is so close to one, up to now, that for a long time, it is going to be available to a computer. So you can prove positively something which, in fact, was always proven negative. So if you are right, that means that the negative result is one implies a negative, and people make the result positive result as well. Okay. Yeah, and that's very this by what you said. The word negative result, and I do that sounds that it's the one that or whether the school square root of 2 is not rational, about you got a positive result. But say no.
Yes, it's true that the results also mean a change in mathematics, but I think this result has an interesting, for example. Let me say, now we can do the study of the developed mathematical knowledge, for example, chronology. According to data. Other kind is about different great works. For example, first Euclides, next the car, next the resolution of the Newtons. But I think maybe in the future, a new way of studying the development of the knowledge maybe could be with investigations, because this study of these results show the connection between different areas and the different concepts. I don't think this is the important of this kind of study, the development of knowledge.
Thank you very much for your talk. I just have two questions or remarks about your use of cornerstone. The first is that it can only be a retrospective concept because you cannot know beforehand if the negative result in mathematics will give rise to what you call a new framework. And the second is, I wonder if there is always a close link between the development of the new framework and the consciousness of the impossibility. Because I think historically, if I go back to your example, you said that in order to square the circle, you need tools like limit or continued fraction. But I think these tools were developed independently from the consciousness of the impossibility to square the circle, though. Or if I take the second example, if memory serves well, there is more positive work done by Lagrange than by Abel in the resolution of equations. Maybe I mean name, sorry.
I don't know. Maybe it's a new idea that could be another 20. It's possible. But I think the line of the research in this world is specific way to show the aspect to show continued results, but I'm not sure if this have another origin for another application. I will think about this. Thank you.
Thank you. Thank you very much, Edgar, for the presentation and the answers.
and then how we keep everyone for the last session.
Okay, I think it's gonna be a kind of difficult because it's okay, okay. So I'm going, the title of my presentation today is From Cyclic Quadrilaterals to the Median Point, Antiparallel Lines in Geometry. So the main topic of my presentations are antiparallel lines, which were coined in 17th century. So I'm going to situate myself in 17th century, and then I'm going to talk to you about the past of the concept and the future of the concept. So that's the idea of today. Okay, well, in order to introduce the topic, let me say that at the last decades of 19th century, modern geometry was just emerging as a new discipline. In this context, where it was consolidated through the publication of books as John Cassius sequel to the first six books of Euclid Elements and Robert Laughlin and Elementary Treatise on Modern Fluid Geometry. And these works are like a kind of extension of elementary geometry, but by dimension of results that are not part of using evidence. That is to say, in the last decades, the mathematicians have been publishing many articles related to many properties of geometric objects, but they were not part of Euclid elements. So in this book, those results were systematized. So in this concept, an initial concept in geometry design starts to appear, and it was the concept of antiparallel lines. Actually, the concept of antiparallel lines was coined in the 17th century, as I said, but it has been not used by many decades. So we know, or I have said many times, that Antoine Arnaud is a mathematician of 17th century who reconstructed Euclidean geometry, and he recognizes many of the most important concepts, relations, typically, but he also proposed new concepts, and antiparallel lines was one of the most important concepts that he proposed. This presentation is divided in three parts. First, I develop some general ideas about the theory of antiparallel lines of Arnaud. Then I examine some antecedents in book 3 and 4 of the Elements of Euclid. And finally, we will see that the concept of antiparallelism was revisited in the last decade of the 19th century. Well, as I said, in the Nouveau Element in Geometry, Arnaud reconstructed Euclidean plane geometry with a method that we can describe as the method of natural order. In accordance with this method, he develops the various books to study the different relations that we can establish between straight lines. I mean, without using properties of plane views, just straight lines. So he studied perpendicularity, parallelism, obliquity, and then he also studied the relation between two pairs of straight lines, particularly the relations of proportionality and reciprocity. And it's in this context that he also developed the idea of the relation of antiparallelism. Well, I'll start with some very simple definitions. So, given four lines, such that, well, first I have to say that Arnaud doesn't distinguish between line and segment. So when I'm talking about lines, I'm really talking about segments. So he says that four lines are reciprocal when if A is to B as C is to D. Well, when four lines satisfy that proportion, he says that A and B are reciprocal to B and C. That is to say that the extremes are reciprocal to the middle. That's just a definition. Okay. Then he also defines antiparallel lines. The definition is very long, so I better try to explain it with this image. For this presentation, I'm going to talk always about a triangle, ABC, and then I'm going to say that lines sorry, this line, P prime is antiparallel to this P with respect to lines AB and AC. That is to say that antiparallelism is a relation between two pairs of lines. Okay, I don't know if does not use that language, but perfectly language, so I'm going to clarify this. So that's the way I'm going to talk about it. So if we observe this triangle, here we have a line that is parallel to the base, and the triangles are similar, we know. But Arnold says that there is another way to construct a similar triangle. That is when instead of drawing a line that is parallel to this P, we draw a line that is antiparallel to this P, which means that it also forms the same angles, but in different orientations. You can see that the only difference is that the orientation is different. Arnold is super establishing so nearly this difference. But I would like to say that Apollo in the comments, when he is studying the different ways of putting a cone, he says that if we put a cone with a plane that is parallel to the base, we find obtain a circle. But he says that there is another way to obtain a circle, and it is by putting the cone with a plane that we could consider as parallel to the plane of the base. So Apollo recognizes very good this property, but in probably geometry. Okay, well, then Arnaud introduced what he refers to as the fundamental theorem of reciprocal and parallel lines, which says there are two, but I only talk about the first. He said when one and the same angle has two antiparallel bases, the full of one and its part are reciprocal to the full of the other and its part. So I will go back to the figure. So it only means that when we have a configuration with antiparallel lines like this one, the tooth AB and its part, which is AC prime, are reciprocal with respect to the other two AB and the other part, which is AB prime. So in terms of proportion, it means that this proportionality is satisfied, which is the same as saying that the product of AB, the tooth by the part, is equal to the other tooth by the part. And this is very important because we will see that this is the property of inner product of, okay, so then Arnaud says that this term is valid when we consider any disposition of antiparallel lines. So we see that here antiparallel lines don't cross the interior of the triangle. Here they cross. Here they share a point. Here they are in different sides of the vertex of the triangle. But actually, I have been working this with Carlos. This together. These four dispositions are actually one, but just that Arnaud is studying by first-time antiparallel lines, so he doesn't make complete abstraction of the properties that actually are the same. So, for example, here what we have is a triangle ABC, and we have a line, and we extend the base. This is the base we extend, and we can take at any point on this line. For example, B prime, and then we can find the antiparallel, which is this dot point, dot line, and this case corresponds to this configuration. But if, for example, we take this point that is here and we find antiparallel lines that go to this point, is this one. So this corresponds to the four cases of Arnaud. So actually, they are the same case. And it is very interesting because actually what Arnaud is telling us is that we can take any point on the line B prime and BG prime, and we always find one and just one antiparallel to that point. And it's interesting because the only case in which we cannot find an antiparallel is when is the point to the infinity. In that case, it will be parallel. So for all other points, we have antiparallel lines. Well, then Arnaud dedicates many pages to study all different possibilities to find antiparallel lines. But I also we can reduce all those cases to two properties. First, I try to explain. First, in this case, in all these cases, we have a triangle, the blue one, KFD, and if we want to find an antiparallel to HG, it will be a line CD, which has the same direction that the tangent at the point K. So any line which we draw will have the same direction that the tangent at the point K is antiparallel. So all these are cases of that property. And in this case, when the point K is outside the triangle or inside the triangle, the antiparallel to FG is the line that joins the other points in which the lines KF and KG put the circle. So in few words, what Arnaud is telling us is that the property of antiparallelism in these configurations is equivalent to cyclic quadrilaterals. So those two properties are all what Arnaud is working through all these configurations, but again, he is just my first time studying this, and this is the form he is studying this. Well, now, we will try to see if, Arnaud is constructing Euclidean geometry. So, what has to do antiparallel lines with the geometry of Euclid? Well, actually, in the elements, we can truly regard, we cannot find a geometry devoted to study the relation between lines. Euclidean geometry is about the properties of plane figures. So, we don't find nothing like a theory of parallels or antiparallels, nothing like that. But we know that Euclid attaches great importance to the study of the parallelogram and consequently to the parallel line. And at the same time, he confers a degree of importance to cyclic quadrilaterals, whose opposite sides, as we have said, are antiparallel. So, but the properties of cyclic quadrilaterals appear only scattered through different books. Their study does not form a unit book. So we will study only, I will talk only about the most important propositions about cyclic quadrilaterals in the book 3 of the elements. And the most important is 322, because Euclid distinguished, Euclid established the distinguishing feature of cyclic quadrilaterals, which is that the opposite angles are complementary in 322. And well, in this case, when we have a cyclic quadrilateral, we have two possibilities. If the opposite sides are parallel, well, this is a square one, an example. But if not, when we prolong, we extend the sides, they intersect. So if you observe, they intersect outside or inside, and we are again in the configurations of Arnaud. So, and Arnaud established what Arnaud told us in all his theory of antiparallels through these two propositions, 335 and 336. No, because actually what he said is that the product of PA and by PB and PB by PC is equal. But he established in terms of the area of the sample, because okay. But this is also what we today know as the inner and outer power of a point regarding to what is different. So, and what is more interesting is that many centuries later, Claudius generalized these properties. These ones are still part of the geometry of areas, are properties about areas in Euclid. Claudius established the relation of reciprocity that Arnaud will develop later. So he says in a sequence to straight lines mutually intersect each other, the segments of one will be reciprocal to the segments of the other. So I am pretty sure that Arnaud read this calling of Claudius, because he's precisely establishing the property of reciprocity, but he's adding a new element that he is defining a new character, which is antiparallel lines. Okay, well, now it could be that what Arnaud did is not very important, because he is just giving a new language to the properties that already are in Euclid elements. But we will see that I have time. Yeah, okay. Okay. But we will see that actually it is important because the concept of anti-parallelism will be rediscovered 2 centuries later in the framework of the so-called new geometry of the triangle of the circle. So at the end of the day, it looks that Arnaud had a good intuition about the importance of characterizing this concept in a different way. So, okay, it says that in the last 3 decades of 19th century, many geometers, and mainly from France and Germany, published articles devoted to study new properties and elements of the triangle and the circle. Florence Cajori says that it is very astonishing that so simple figures of the triangle and the circle, which have been extensively studied by many centuries, were revisited and new properties were found. So in this concept, a French mathematician and engineer, which is called Emile Moine, started to use again the concept of antiparallelism. And actually, there was a debate in this epoch about the origin of this concept, and they actually put this origin to Leibniz. And we know that Leibniz read this from Arnaud, but nobody mentioned Arnaud in this discussion. They think that the first who used it was Leibniz. Okay, well, and also it's important to say that after this decade, the concept of anti-parallelism was incorporated in some textbooks, mainly in English language, which shaped what we now understand by the modern geometry. Okay, so the works of Lemoine, Ferrari, and Parallels are divided into periods from 1873 to 1875, and later to 1883 to 1886. In the first period, Lemoine focused his attention on a new notable point of the triangle that we now know as the Lemoine, and also is known as the Simonian point. I will talk to this later, so just some of his works were sur quelques propriétés d'un point remarquable et d'instable, nous sur un point remarquable et plan d'inconable, et nous sur une propriété du centre des médias antiparallèles d'un multivariate. And in the second period, he started studying another properties, also related to this, but also related to the characterization of geometric space, geometric logic, to the use of parallel and antiparallel lines. So some examples from that period are quelques properties de parallèles and antiparallèles du côté d'un triangle. Okay, so I'm not, this is the definition of antiparallel lines of Lemoine, but I will not repeat because he's just simply telling us in another way that two pairs of antiparallel lines form a specific quadrilateral. These properties are equivalent. Okay, but Lemoine defines another element of the triangle, which is called antiparallel median, and which is a line that goes from the vertex of the triangle, any vertex, for example, the vertex A, to the middle point of the antiparallel. It's important to say that both antiparallel B prime C, B prime C, B prime, B prime B prime C strong, antiparallel to this thing. So the median, the antiparallel median is a line that bisects all those sectors. And this is called antiparallel median. So in the same way that the classical studies of the triangle use the concept of medians, propose the idea of antiparallel median, and they are later called symedian, and I will tell you why. He also proved that the three antiparallel median of a triangle intersect at a point in the same way that when we consider the two medians of the triangle, they intersect in a centroid or right center. So what we are observing is that a new characterization of the triangle is constructing about the idea of a new concept, which is antiparallel line. So, okay. Well, after he describes antiparallel lines, Simonian lines, and the Simonian point, he obtained other much more complex results involving those elements in connection with conics and in particular with circles. For example, this is called the first Lemon circle, and here we have a triangle ABC, and we have this median point F, and we draw lines which are parallel to the sides of the triangle, which go to the median point, and it results that the 6 points in which those lines intersect the triangle are positive. So we start with cyclic quadrilaterals, and now we have cyclic hexagons. So also it's notable that the segments 1, 2, 3, 4, and 5, 6 are antiparallel to the signs of the triangle. Well, this is the second one, but I just forget. Well, another observation is that antiparallel lines, as well as the median point and the median line, are notable elements of the triangle that have a certain relation of symmetry with the classical elements. So, for example, if we take the parallel to BC by the point O and the antiparallel, they are symmetric with the receptor of the angle A. Also, the median and the median lines are symmetrical with respect to the receptor of the angle A. So, what here the one is constructing a theory focusing on some symmetric elements. So, some concluding remarks, as Norton related the concept of antiparallel lines in the mid-17th century, largely as a result of the organization of geometry and the study of the ways in which straight lines can relate to each other. However, the property underlying the concept of antiparallel lines, that is the property of possibility of a quadrilateral, dates back to the element. In Euclid elements, simply quadrilaterals are also important. However, they are not like a very, very important configuration. But even though 322, 334, and 336 are all necessary for Arnaud to develop later the theory of antiparallel lines. In the 18th century, this concept was discovered, but in the context of a new theory, which was the new geometry of the triangle. Antiparallel lines open the door to visualizing and studying the triangle to the elements that are symmetrical to the classical notable elements. And Lemon makes the concept of antiparallelism key focus of his research, and he finds many relations that I didn't talk about, but he related this concept with homotopy configuration with the one sequence, geometric velocity, also is related to inversion, and there are many properties. Today, we can see in modern geometry textbooks that the concept of antiparallelism is linked to topics of great importance, such as radical axis, partial circles, inversion, the circle of 9 points, and so on. Thank you. Other questions?
Thank you very much. And first of all, you remember when we discussed about the antiparallel, that was an interesting point to pursue. The thing that related what we said about computation quite recently. There are computations which still in the bonus and the proportion theory. Almost all what you did could be done only with angles.
Yes.
So when you consider angles, you look at angles. You don't compute, you have inequalities, you compare on a circle, simply and so on. It means you have a situation and you try to do whatever you may think in terms of precisely not measuring what you are doing, but locating them. From the axis, it has been part of geometry up to now. After all, when you look at the problem about having straight lines, symmetric to the bisectors and so on, I mean, problem, you don't compute it. It's prime, except that the method is described only with angles on the surface. So, well, I wanted to make the relationship with what we say about action. Okay, thank you.
So I think what is relevant of this new theory of anti-parallel lines is that we consider the same element that situated in a different purpose. So we could actually, I have been thinking many times that we could omit the theory of anti-parallel lines because at the end we are just, as you say, working with angles, but we are inverting the position of the angles. But I think that the fact that anti-parallel lines recite a name, they are established like a concept, make it easier to work with this concept and the creation of new concepts like Simonian point. So I think that is like an heuristic way of making it easier to think about other properties of it. Thanks. So, question. Get it done. I want to say
Well, no, it's just a very, very nice question. And which is somehow related to the previous talk in the following sense. What we heard from the previous talk, and what we agree that negative proofs, negative theorems, negative statements somehow open new frameworks, I might say. I think that it showed, maybe I did not understand well, it didn't show any negative result. Everything here was positive. From Euclid, Arnaud, in the 19th century. And one of them, I think all of them, if they were together, maybe they are together now, we have discussed it, enjoying that they can be together. We don't have, but but somehow it's clear that their framework, their respective frameworks, are not the same. So new frameworks have appeared, but not because from negative thought, some obliged create a new framework. So it's just a question. What do you think?
I'm thinking that if two triangles are similar, but the bases are not common, yeah. Because we are analyzing two triangles which are similar, but a property, they are not defining a property which is defined of the base. I mean, it's not the same as what Edgar talked about.
Well, it's very interesting, Josephine. It's very interesting because compare the definition of anti-parallelism with the theorem de Taille. That's for sure. But that I don't think it gives us negative results.
No, you want to say something else?
It's no more questions. We can put the next question. Thank you again.